today we will be talking about energy savings that are possible using compression cores in IoT devices. I want to go back to the basics and let's first define what IoT is. In my opinion, IoT today is the next big wave that all IT vendors want to ride so that they can make more money. That's the definition. In other words, or from a different angle, you can say that IoT is a network of physical objects or things which collect and exchange data without human interaction. And we all agree that this is booming, and Cisco says that we will have 50 billion things by 2020. Some other people say it will be 25. The bottom line is that we're going to have lots of them. And most of these things would be the IoT nodes. Okay? There's also obviously an effect on the network infrastructure and all that, but IoT nodes is what our industry is mostly after. So, what is a typical IoT node? Well, that's a pretty abstracted picture of what that is. But in general, you have sensors, you sense some type of physical effects, and you may also have actuators so that you can control a step motor or whatever. And you have a microcontroller type of chip. It could be more complex or less complex. So you have a CPU or CPUs, you've got memory, you've got peripherals to communicate with your sensors and your RF, and you have accelerators. They could be for security, they could be for accelerating DSP functions. You also need to communicate with the world, and RF is the most common way. So you have some transceiver for ZigBee, BLE, 802.11ah, whatever that is. And then you have an NVM memory, and I would include in the NVM definition the embedded flash too. So you need to store your firmware somewhere. And all this needs to be powered by a battery for a long, long time, or it needs to harvest energy from the environment and operate. And most of the time, this type of devices will be sleeping, and sometimes they will wake up, sense something, or do something, and then go back to sleep. So in general, low energy consumption is a key factor here. And we have heard what Synopsys does to optimize energy, and there's a lot of activity out there. Today I'm going to say something that is, I'm going to present something that is sort of orthogonal to all those. I mean, it can be applied as a complementary thing to everything we do. But before we go there, let's see where energy is really consumed. And I'll just take some typical characterization numbers for our building blocks. So a low power CPU itself consumes something in the order of 0.1 to 1 milliampere when active. So a Cortex M0, if you go at ARM's website, it will tell you, if you can do the math, it's 25 milliamperes when active. The B820, which is our processor, is of course more low power. It's about half that power consumption. But then when you look at a microcontroller with all the peripherals and such, that might grow by a factor of 5 or even 10. So let's say that your MCU in our diagram is about half a milliampere or 5 milliampere when active. So let's go to our next modules. You go to the RF part and you get scared. I mean, if you're only receiving data, you could be okay. But at the time you need to transmit data, it can get really ugly. So I have here some numbers for transceivers that are today promoted like low power RF transceivers by TI and Semtech. So 2.4 gigahertz, 14 to 19 milliamperes while receiving, and 11 to 29 in transmission mode. So quite a difference from our MCU itself. Now Semtech, which is a different frequency range, if you want to transmit depending on how far your signal wants to reach, you can go up to 126 milliamperes. Okay? So this is the hottest part of our IoT node. But then also the NVMs are power consuming. I have the example of serial flash here. And serial flashes are 2 to 25 milliamperes. They're widely used today, but even embedded flashes in the order of a few milliamperes, okay? So they cannot be ignored. Now, numbers again, 2 megabit micron serial NOR flash at 75 megahertz. Read kernel is 12 milliamperes, quite a big number. Macronics at 8 megahertz. Those devices can operate at different frequency ranges. I just picked random points. It's 3.5 milliamperes. So RF transceivers, most importantly, but also NVMs are major energy consumers. And we can actually reduce those, the contribution of those two elements by using compression. And the basic idea is pretty simple. So consider the case first that we have our firmware being compressed, stored in the NVM. So if it is compressed and we decompress it on the fly, that means we are accessing that NVM less time when we wake up or boot, okay? And that is actually lower energy that translates to lower energy to wake up or boot. And by the way, because you have lower access and those NVMs are slow, it also probably leads to smaller wake-up time. Now, similarly in the RF side, if you compress the data you have to receive or transmit, you need your RF to be active for smaller time, and then that means you're consuming less energy for communicating data. So, what are the expected energy gains? Can we quantify them? And what are the overheads to achieve compression on our typical IoT device? So, we want to add the compression capability to our sample IoT node. The first question is, what kind of compression do I need? So we will have to go with lossless compression because we don't want to lose our valuable data that we want to communicate. And then we want something that is widely used so don't face interoperability issues. And GZIP has been used for ages. Now it seems to be the obvious way. The next question is whether I'm going to do that in software or hardware. My point of view is that a hardware accelerator, if it is small enough, it doesn't consume too much area, too much silicon space, it's probably a better idea because it's going to consume lower power to actually implement the compression, and it's not going to throttle your CPU because compression is computationally intensive and it could overload your CPU. So we have our architecture in our IoT node, and we want to see what would happen if we use that type of an accelerator for firmware decompression while doing code shadowing, reading from the NVM and bringing that on a local SRAM, and and compressing data and what we want to communicate via an RF network. And that you can do at different levels. So you can actually compress data on the application level or as part of your network stack by protocols like IP, COMP, and so on. But regardless of how you want to do it, you can always use the accelerator there. So what are the expected energy gains? I'm running a bit fast as we're running late. Everything will depend on compression ratio, how much I can compress my data. And the compression ratios would depend on the algorithm itself, its parameters, and the data characteristics. Not all data are equally compressible. On the GZIP world, you have practically two main choices. You have to decide whether you want to have a static or dynamic Huffman engine. And static Huffman leads to smaller silicon, dynamic is leading to higher compression. There's a trade-off there to be made. The history window is like deflate, which is the base of GZIP. You look back in the history to find a good match of your current data, so that you transmit a pointer to that as opposed to the data itself. So the smaller history, again, you need less memories to store that data, less silicon. The larger the history, you get higher compression, so possibly higher energy gains. So someone will need to play around and see what suits its needs of its specific application. But in general, I think keeping silicon overhead low would lead in most cases in using static Huffman and relatively small history windows. Now, okay, we chose GZIP, we've seen what are the parameters now. How compressible are our data? So we want to compress data that we transmit over RF networks. These are typically a set of measurements out of a sensor, maybe some commands to the device, or HTML type of pages that allow configuration of the device. So these type of data, which resemble text files or spreadsheets or things like that, are highly compressible. And you can easily get levels to 3:1, compression level to 3:1 for both even for static Huffman tables and small windows. And there's a lot of people and a lot of results out there in the web that you can find references for that. But the bottom line is that these are highly compressible type of data. Now, firmware is a different thing, because firmware, by definition, when you develop an instruction set, you're not wasting bits. So it's more random data in a sense. To get an idea of what is feasible, we have run experiments using 3 different targets. A BA22 processor, an 8051, and a Cortex-M3, so 3 different instruction sets. And we have chosen what we consider being representative examples of the code that our node could run. So it's a sensor control application over FreeRTOS for the BA22. It's again a FreeRTOS type of application on the 8051, and it's intermisses TCP/IP and HTTP stack for the Cortex-M3. So we compile them, we compress the firmware, and here's what we get for static Huffman and 3 different history sizes, which are on the smaller side of things. And we've done more experiments on that, but the bottom line is that even for those, you see that you can get close to 2:1 in most cases. It goes up and down depending on the application and the instruction set itself, but 2:1 compression is still there. And that's not too low. Whoops, that is messed up. Well, I will not worry about that. So what we have done is we try to translate that to actual energy numbers, okay? So we made the assumption of static Huffman and 2 kilobytes of history, and we've made the assumption that we've got a 1.8 volt NVM with 5 milliamperes read current, operating on 50 megahertz. And then for the 3 cases, we counted code size, the required NVM size, the boot time, and the energy. And I will not go here, but in most of those cases, you get a 2:1 factor reduction. So you went down from 1.39 millijoules for this one, which is the Cortex-M3, the TCP/IP stack on Cortex-M3, to down to 0.72 millijoules. And that's important. I mean, that's 700 microjoules difference almost. Boot time, again, about a half. So there are important savings there. You can get really nice savings both in energy and in boot time. Now, the other type of example that we wanted to see is, okay, what happens if I compress my RF data? So in order to quantify again what we are discussing about, we are assuming an RF transceiver with 30 milliwatts active power and 2 milliwatts idle power, an MCU with 2 milliwatts active power and 0.3 nanowatts of idle power, and a GZIP accelerator core from CAST. And here we have our energy consumption of our system for different duty cycles. And duty cycle being the number of seconds that our device is active within an hour. And obviously, the more active we are, the more we're consuming energy over time. So these on top are the numbers we had before, and now we are making the assumption that we are achieving a compression ratio of 2:1 of the data that we're transmitting. And obviously, the savings that we get out of our RF engine are greater when we have the RF engine working for longer times. So we start from about 48.5% in our example down to 1.8% when our duty cycles are pretty small, some microseconds every hour. So still, not a solution for every device, but for specific devices, significant gains could be there. I'm running quickly, not to waste time. So, but in conclusion, compression can be used to significantly reduce energy consumption in IoT nodes. Firmware compression and data compression for the RF communications are just two of the ways. You have to take into account a few parameters before you make the decision. You have to choose your compression algorithm and parameters. You have to check the compressibility of the data you have, and you have to do obviously an energy profile of your system, taking into account duty cycle. And for this type of things, we have at CAS we have a set of GZIP and GZIP cores that are perfectly suitable. And this is because we have configurations of those cores that have very low latency, down to 20 cycles, so they don't delay things. Okay, 20 cycles latency first in to first out is like 0. They are pretty small, like 20,000 gates, 22,000 gates. Nothing major. Again, for static Huffman and small window sizes. They are pretty low power. Throughputs can be at a level of 160 megabytes per second when clocked at just 10 megahertz. Now, if we're talking about RF compression, when you only need to transmit 1 megabit, which is pretty high for many IoT devices, that means that you can actually clock the accelerator at the kilohertz range. So active power is pretty low. And it's very easy to integrate because we have bus interfaces, streaming, AXI streaming, or normal AHB and AXI interfaces. And that was all. Thank you for your attention.